discuss part C, section C of our first internal. Question 9. Data quality issue in feedback analysis. Discuss data quality issue, accuracy, completeness, and consistency in feedback analytics. Proposing two other dimensions of data quality relevant to learning analytics. First is accuracy. Data reflects the true state of feedback issue. Contradictory ratings. Example, a student rates a faculty member as 5 by 5 for knowledge but 1 by 5 for teaching style. Impact lead to misleading features, vectors, and poor model training. Second is completeness. All necessary data is present. Issue missing survey responses. Example, a student fills only half the questions. Impact it is statistical power and requires imputation which introduces bias. Third is consistency. Data is uniform across the dataset. Issue inconsistent rating scales. Example, one department uses 1 to 5, another uses 1 to 10, or it uses text labels like high low. Impact prevent direction comparison and aggregation of data without standardization. Fourth is additional dimensions for learning analytics. Timeliness. Feedback must be recent enough to be relevant. Example, feedback from a course 5 years ago is less relevant than last semester. Validity. Data measures what it is intended to measure. Example, ensuring a course rating truly captures courses quality, not just the student's mood. Question 10. Handling missing feedback values. Question, discuss approaches for handling missing student feedback values. Example, constant mean mode imputation, class specific imputation, or most probable values. So A. Constant imputation. Fill missing values with a designated constant. Example, 0 or a value outside the typical range like -1. So use case when missingness itself is a feature. Example, did not answer means indifference. B. Mean mode imputation. Replace missing numeric values with the column mean or nominal values with the mode. Use case simple, fast, and maintain the overall mean mode of the attribute. So question reduces variance and introduce bias if missing data is not missing at random MAR. C. Class specific imputation. Impute based on the mean mode of the specific class or a group the student belongs to. Example, mean rating from a student in the same department of the year. Use case exploits domain knowledge more accurate than global imputation as it uses local characteristics. D. Most probable values imputation. Example, using regression or KNN. Use a predictive model like linear regression or k nearest neighbors to estimate the missing value based on other complete attributes in the profile. Use case high accuracy, preserve covariance structure better than simpler method. Question computationally expensive and complex. So question 41. Feedback rating smoothing the and outlier detection. So A. Smooth the rating using bin means with bin depth 3 illustrate steps. Solution. Bin means smoothing depth 3. Data from question to 13, 16, 18 and to 70. So first step 1 sort data. Yes, it is already sorted. Second, determine bin depth and size. So depth d is equals to 3, total values n is equals to 22, number of bins is 22 divided by 3 is equals to 8. So partition into bins size 3 or less. So bin 13, 16, 18, mean 15.67, in bin 2 19, 20, 19, 20, 20, mean 19.67. So here is the bin 2 7 which is 556.00 and bin 8 no remaining values. If we assume only the first 21 values we had have 7 bins exactly but 22 values means 8 bins. If the last bin is size 1, let's assume the list size of 22 is correct. If the list had 21 values, example stopping at 52, the 7 bin would be full. Given the original data from question 2 has 22 values, the bins are as shown above. Fourth, smooth data. Replace bin values with min. So bin 1, 15.67, 15.67, 15.67, bin 2, bin 3, bin 4, bin 5, bin 6 and bin 7. So B. Suggest ways to detect outlier. Example, abnormally high or low satisfaction. Solution, outlier detection method. First is box plot or IQR method. Description, calculate the Inter interquartile range IQR Q3 minus Q1 value falling outside the fences lower Q1 minus 1.5 IQR and upper Q3 plus 1.5 minus IQR are flagged as outlier. Use cases simple effective for univariate data and robust to extreme value. So second is Z-score method. So description. Normalize data using the z-score formula. Z is equals to x minus mu divided by sigma. Any data point with a mod z is greater than threshold typical 2.5 or 3 is an outlier. So use case. Effective if the data is approximately normally distributed, less robust if the distribution is skewed. So third is isolation forest or local outlier factor. Description: machine learning techniques that identify points that are isolated from the rest of the data, isolated forest, or that have significantly lower density than their neighbors. Use cases: ideal for multivariate data and complex distribution where simple statistical rules fail. C. Discuss other methods for data smoothing. Solution: other data smoothing methods. First is bin boundary smoothing. In each bin, replace all values with the closest bound. A, array min or max values of that bin. Bin median smoothing. Replace all values in bin with the median values of the bin. More robust to outlier than bin means smoothing. Third, regression curve fitting. Use linear or polynomial regression to fit the data. The smooth value is the value predicted by the fitted line curve. This help identify trends and remove random noise. Fourth, moving average. Replace each data point with the average of itself and its neighbors within the defined window. Mm, So, question 12 in data integration for MCM tag analytics, discuss schema integration, handling redundant data, example, duplicate entries from multiple servers and resolving conflicts in values. Solution: data integration issues. First is schema integration, the process of combining schema from multiple data sources into a coherent global schema. Issue: entity identification problem. Example, faculty ID in one system is instructor code in another. Resolution: use metadata matching, entity resolution techniques, and data dictionary alignment to map equivalent attributes and resolve homonyms, same name, different meanings, and synonyms, different names, same meaning. Second, handling redundant data. Duplicate data can be derived from other data. Issue: duplicate entries. Example, the same student submits feedback twice or a course ID is stored both as course ID and course key. Resolution: perform correlation analysis to identify derivable attributes. Uses tuple comparison to find duplicate records. Prioritize one source as the master or compute an average consensus value. Third, resolving conflicts in value discrepancy in attribute values across different sources for the same entity. Issue: contradictory feedback. Example, survey A rate faculty at 4 5, a survey B rate them at 2 by 5 for the same period. Resolution: use consensus method. Example, average weighted average based on source reliability, or use time stepping to prioritize the most recent data. Question 13, 14 normalization method and calculation. Question 13. Discuss normalization method. A. Min-max normalization. B. Z-score normalization. Z-score normalization using mean absolute deviation decimal scaling. A. Min-max normalization. Rescale data to a specific range, typically 0 to 1. Formula is V minus min A upon max A minus min. Second, Z-score normalization. Standardized data to have a mean of a 0 and a standard deviation of 1. So formula is V minus mu of upon variance of a Z-score normalization, mean absolute deviation, less sensitive to outlier than using the standard deviation. So this is equal to V minus mu upon MAD. So D, decimal scaling, normalized by moving the decimal point based on the maximum absolute values. This is equal to V upon 10, where J is the smallest integer such that maximum of a mode of V dash less than 1. So question 14, normalized faculty workload values. So workload hour per semester. Here is the workload hour per semester using A minus D data. A 200, 300, 400, 500, and 1000. So minimum 200, maximum 1000, range 1000 minus 200 is equal to 800. So A is equal to 2500, mu is equal to 2500 divided 5 is equal to 500. Mean max normalization range 0 to 1. So here is the value. By doing calculation, V is equal to 0.0, 0.125, 0.25, 0.5 and 1. So Z score normalization standard deviation. So here is the formula for Z score, and by putting values in it, we get 2 at 2.84. So here is the table. So values and calculations, and here is the V. So C, Z score normalization, mean absolute deviation. So mean absolute deviation, here is the formula for it, and MAD, by putting values in it, we got 240. So here is the values, and here is the calculations, and by putting in it, here is the values of V 1.25, 0.83 to 2.08. And D, decimal scaling, makes V is equal to 1000, find smallest j such that 1000 divided by 10 j is less than 1, j is equal to 4, 10,000, 10 to the power 4 is equal to 0.1 less than 1. So j is equal to 4, v dash is equal to v divided by 1000. So v and v dash is equal to v is equal to 200, v dash is equal to 0.2. By putting the values of v in this formula, we got the value of v dash, and so on. So question 15, normalize feedback rating values. Okay, rating value. Feedback rating values 1 to 5 range 1, 3, 5, 5, 5 using A minus D. Data 1, 3, 5, 5, 5, n is equal to 5. So min is 1, max is 5, range is 4. So summation of B 19, mu of B 19 by 5 is equal to 3.8. Sigma of B is equals to 1.6, and MAD is equals to 1.44. And a min max normalization range of 0 to 1. So here is the values by doing calculation. V dash is equal to 0.0, 0.5 and 1. So Z score normalization, here is the values by doing calculation. We got V dash is equal to 1.75, 0.5 and 7.0.75. So C, Z score normalization, MAD is equal to 1.44. So here is the value, and by doing the calculation, so we got the V dash by putting the values in this formula, and decimal scaling, maximum and smallest j such that 5 divided by 10 j less than 1, j is equal to 1, 5 divided by 10, 5 less than 1. So j is equal to 1, v dash is equal to v divided by 10. So here is the values of v and v dash. And question 15, they discuss which method is most appropriate and why. So most appropriate method, min-max normalization reasoning. Feedback ratings inherently use a bounded linear scale 1 to 5. Min-max preserve the relationship between the ordinal values while scaling them to a uniform, easily interpretable range like 0, 1 or 0 to 10. This is crucial because a rating of 5 is always the maximum possible satisfaction, why other are less suitable. Z-score methods B and C lose the boundary information. A Z square can be arbitrarily large or small, which is meaningful for a rating scale that cannot exceed 5. Decimal scaling D result in a narrow range of values 0.1 to 0.5, which offers no differentiation for a model. Here is the question 16, age and productivity normalization. Using age and productivity from question 4, normalize both attributes using Z-score normalization. Data from question 4, age is equals to 1, 23, 27, 27, 39, 41, and here is the data to 61, n is equals to 18, and productivity P is equals to 26.5, 7.8 to 31.35.7, and n is equals to 18. So age normalization, mu of is equals to 44.83, calculated from question 4. See, and here is the variance of 12.94 given in question 15 but derived from the age data. So Vedic age minus 44.83 divided by 12.94. So here is the original age, here is the difference, and here is the Z score. And then productivity normalizations, mu p is equal to 30.65 and sigma p is equal to 10.66. By putting v dash p is equal to productivity minus 30.65 divided by 10.66. So here is the original product and difference and then G score. Question 17. Person correlation and covariance. So compute person's correlation coefficient and covariance on the student project evaluation score 5, 10, 11 to 215. Comment on whether the relationship is positive or negative. The question provides only one set of score H 5, 10, 11 to 215. Since only one variable is given, a correlation or covariance calculation is uh, one impossible. The questions likely intend to ask for the five number summary or mode mean, median, standard deviation to characterize the single distribution. If the intent was to characterize the distribution of x data x is equal to 12 values, mean is equal to 7 for 7 divided by 12, 62.25, median 35 plus 50 divided by 2 is equal to 42.5, standard deviation sigma of x is equal to 77.8. And the question intends to amplify correlation with an implicit second variable. Example x score is equal to 5, 10 to 1, 5, y range 1 to 12. Covariance. Measure the joint variable of two variables. Co x y is equal to x minus mu x y minus mu y. Since the score is x are monotonically increased except for minor difference, the score increases with rank 1. Therefore, the product of the deviation will generally be positive, leading to a positive covariance. Now we will discuss part D of our first internal. So question 19. Student collaboration dataset analysis. So student collaboration dataset. The dataset defines student skill is asymmetric binary variables. P is equals to 1 for position, N is equals to 0 for absence, gender is symmetric. So student, their gender is skill 1, skill 2, skill 3 and skill 4. So P1 is equal to positive position, N is equal to 0 negative absence. 19. Construct contingency matrix for AB, AC and BC. So we define the counts for the four possible joints. Outcome Q. Number of variables where both students have P11 R. Number of variables where student 1 has a P and student 2 has N10. S. Number of variables where student 1 has N and student 2 has P01 and T. Number of variables where both students have N00. Note: for asymmetric attributes, the joint absence of skill is often ignored. Here we calculated only for the four skill attributes A 0110 versus B 0101. So Q11 skill is equal skill to 1, Q is equals to 1. Here R is equals to 1, S is equals to 1 and T is equals to 1. So contingency matrix AB. So A P of 1, A N of 0, B P of 1, B N of 0, Q is equals to 1, S is equals to 1, R is equals to 1 and T is equals to 1. So A 0 1 1 0 versus C 1 0 0 1, Q is equals to 0, R is equals to 2, S is equals to 2 and T is equals to 0. So here is the contingency matrix for this, and B 0 1 0 1 versus C 1 0 0 1. So in this the value of Q is 1, value of R is 1, value of S is 1 and value of T is 1. For this the continuity matrix B and C is this. And now 19th B, compute invariant dissimilarity. For asymmetric binary attributes, the invariant dissimilarity Jaccard dissimilarity is used, which excludes T-joint absence from the calculation. So dissimilarity Ij is equals to R plus H divided by Q plus R plus S. So A versus B, dissimilarity AB is equals to 1 plus 1 divided by 3, which is 2 plus divided by 3 is equal to 0.667. A versus C, here we put values go to 1. B versus C, when we put values we got 0.667. So 19th is come to non-invariant dissimilarity. Non-invariant dissimilarity, simple matching dissimilarity includes T-joint absence, which is appropriate when all variables include the absence of a skill are considered equally important. Dissimilarity Ij is equals to R plus S divided by Q plus R plus S plus T. So total attribute Q plus R plus S plus T is equal to 4 for skills. So A for A versus B is 0.500 and A versus C, which is 1, and for B versus C is 0.500. Now 19th D suggests the best and worst student collaboration pair. Based on invariant dissimilarity skills only, pair AB, AC, BC, dissimilarities, here is the similarities and here is interpretation. So for AB, moderate skill match, and for AC, no skill match, and for BC, moderate skill match. So recommendation, skills only. Best pair, highest skill match, AB and BC both have similarity of 0.333. They have one shared skill and two unshared skills. So worst pair, lowest skill match, AC, dissimilarity of 1000. They share zero skills, Q is equal to 0 and differ on a skill where at least one of them has possession. So 19th C include gender in analysis and re-evaluate compatibility. So gender is a symmetric nominal variable. We use the simple matching method for the overall compatibility which includes gender and all four skills. So dissimilarity number of mismatch divided by total attributes. So gender attribute mismatch, AM versus BF mismatch, AM versus CM match, BA versus CM mismatch. So A versus B, gender mismatch 1, skill mismatch R plus S 2 from 19C, total mismatch 1 plus 2 which is 3. Dissimilarity 3 divided by 5 is 0.60. Similarly for A versus C, gender mismatch 2, skill mismatch 4, total mismatch 4, dissimilarity 0.80. Similarly, B versus C, gender mismatch 1, skill mismatch 2, total mismatch 3, so dissimilarity is equal to 0.60. So final compatibility reevaluation, simple matching on gender plus skill. So here is the pair, dissimilarity, similarity and interpretation, moderate compatibility, low compatibility and moderate compatibility. The recommendation, gender plus skill. Best pairs are highest compatibility, AB and BC, similarity 0.40. They have the lowest total dissimilarity. And worst pair, lowest compatibility, AC, dissimilarity 0.80. This is due to their extreme difference in skill possession. R plus S is equal to 4. So conclusion, including gender did not change the relative